partial F statistics. Today we will discuss first partial F statistics. It is our full model. Y curl of order n cross 1, x n cross p, beta curl p plus 1 plus vector of error component epsilon curl. Suppose we have k explanatory variable then p equal to k plus 1, where this one for intercept term. Now we partition X matrix as x1, x2, where order of x1 is n cross p minus r and order of x2 is n cross r, n cross r. Now the claim is these are explanatory variable which comes from x2 contribute significantly to the regression model. Therefore, our null hypothesis H naught beta 2 curl, this is beta 2. If we partition beta curl as beta 1 curl prime, beta 2 curl prime, whole prime, then since these are explanatory variables, we want to check whether this R explanatory variable contributes significantly to this model, then our null hypothesis should be beta 2 curl equal to 0 curl versus alternative hypothesis beta 2 curl not equal to 0 curl. So, OLS estimator for this full model beta curl hat equal to x prime x inverse x prime y curl. And SS, that means sum of square due to regression for this full model equal to beta curl prime x prime y curl. This is equal to y curl prime x prime x inverse x prime y curl. We write it as y curl h y curl. This h is nothing but this portion. That is h equal to x prime x whole inverse x prime. And corresponding degrees of freedom for this full model equal to, since there are k regressors or explanatory variables, so degrees of freedom is for full model is equal to k. Now under H naught, the reduced model is y curl n cross 1 x1 beta 1 curl plus delta curl. Then OLS estimator for reduced model is equal to x1 prime x1 inverse x1 prime y curl, and SS due to regression for this reduced model is equal to beta 1 curl prime x1 prime y curl. So we write it as y curl prime h1 y curl, where this h1 is x1 prime x1 inverse x1 prime. Now SS due to residual for full model equal to y curl prime y curl y curl prime hy curl, that is S is due to regression, y curl prime I minus h y curl. We denote this I minus h equal to h bar. So we write it as y curl prime h bar y curl. Now define SS due to regression beta 2 curl given beta 1 curl. This is equal to the sum of squares of regressions due to beta 2 curl given that beta 1 curl in already in the model. So this is equal to sum of square due to regression for full model minus sum of square due to regression for reduced model. So this is equal to y curl prime h y curl minus y curl prime h1 y curl, where h equal to x prime x whole inverse x prime and h1 equal to, where h equal to x prime x inverse x prime and h1 equal to x1 prime x1 prime x1 inverse x1 prime. So this equal to y curl prime h minus h1 y curl equal to y curl prime I minus h minus I minus h1 y curl equal to y curl prime this is equal to I minus h1 minus I minus h y curl. So this is equal to y curl prime I minus h1 y curl plus minus y curl prime I minus h y curl. So this is nothing but a sum of square due to residual for reduced model, and this is nothing but a sum of square due to residual for full model. Therefore, sum of square due to residual beta 2 given beta 1 is equal to sum of square due to residual beta 1 curl minus sum of square due to residual beta curl. And the degrees of freedom is equal to P minus R, that is equal to R. So sum of square due to residual beta 2 curl given beta 1 curl is nothing but a measure of regression sum of square that result from adding the So SS due to regression beta 2 curl given beta 1 is a measure of regression sum of square that result from adding the explanatory variable xk minus r plus 1 xk in the model when the model has already x1 x2 xk minus r explanatory variables. Therefore, test statistics equal to if not SS due to regression beta 2 curl given beta 1 curl by its degrees of freedom whole divided by SS due to regression SS due to residual for full model divided by its degrees of freedom n minus p. So this is equal to n minus p by r into SS due to residual for reduced model minus SS due to residual for full model divided by SS due to residual for full model. We assume that expectation, we assume that y curve follow multivariate normal with mean vector x beta curve and dispersion matrix sigma square in, and under H naught y curve follow multivariate normal with mean vector x1 beta 1 curve sigma square in. And since we know S is due to regression for full model and S is due to regression, S is due to residual for full model are independent. So S is due to regression for full model minus S is due to regression beta 1 curve for reduced model and S is due to residual beta curve are also independent. Since this portion is same as this portion, sum of square due to residual beta 1 curve minus sum of square due to residual beta curve, and this is equal to sum of square due to regression beta 2 curve given beta 1 curve. So we conclude that sum of square due to regression beta 2 curve given beta 1 curve or sum of square due to residual beta 1 curve minus sum of square due to residual beta curve or sum of square due to regression beta curve minus sum of square due to regression beta 1 curve and sum of square due to residual beta curve are independent. Hence, under this condition, this follow a distribution with Rn minus p degrees of freedom under H naught. Therefore, we reject H naught at level alpha if f naught greater than f alpha r n minus p. This is the upper percentile, alpha percentile point of f distribution with r n minus p degrees of freedom. This f naught is called partial f statistic, and this is a measures or this f naught measures the contribution of explanatory variable in capital X2 given that the other explanatory variable in X1 are already in the model.